So I am the COO of Renaissance Fusion. We're a startup based in France. And in a nutshell, I would like to show what we do. As I mentioned before, the three keywords are stellarators, high-temperature superconductors, integrated with liquid metals. The basic idea is stellarators are complex, but we have a simpler way to build coils. You can see at the bottom right the complex shape of the blue coils that we build today compared to a simpler approach that we want to implement. How do we do that? By making our own HTS superconducting tapes, and we change the paradigm of how we make them. On top of that, we integrate all of this with liquid metals, and our view is that the liquid metals will resolve all the problems that concern the breathing and the breathing blanket that we've been hearing about through all the morning. How do we do that? We build stuff. These are our labs, and you can see this is an example of a film deposition machine that we'll use to produce our HTS tapes. In the middle, we have an experiment where we tested a first liquid metal solution. We want to use the liquid metal to protect the solid phase, solid walls, and so the liquid metal is the first item that is in front of the plasma. You can see a slice of the reactor in here. And the last point is, how do we simplify coils? We basically paint tapes. We use these tapes to roll them around the vacuum chamber, and then we draw the shapes of the magnets on top of these tapes. And so instead of having discrete coils, we have continuous carpets, as we call them, which makes it much simpler when producing them. This was just a general overview of what we do. Now, if you look at HTS technologies and how they can lead to spin-off opportunities, this is a bit in deeper detail how things are done today in the HTS industry and how we plan to do things, as I mentioned a few minutes ago. So today we have narrow tapes, 1 centimeter wide, which are based on, let's say, steel at the beginning, and then you deposit one on top of the other, a number of layers, including, it's a bit tiny, but there is one specific, which is the dark one, which is the superconducting layer. So that's where actually the current is flowing. Once you have a tape, which is 1 centimeter but tens of kilometers long, you have to stack them and fit them into a cable structure. And the cable, of course, needs to be mechanically and electrically protected and supported. Once you have that cable, you have to wind them to make a coil, and you can see the shape of the coil being a 3D sculpture makes the winding not easy. And finally, once you have the coil, you have to fit the coil and make it go through, well, actually around the vacuum chamber. Again, sub-millimeter precision with pieces of equipment which are very fragile and very heavy. The change of paradigm that we want to put in place is that, as I mentioned before, we don't have the tape, we don't have the cable, we go straight from depositing on a carpet, which is 1 meter wide, so the paradigm is from 1 centimeter to 1 meter, and that will be the base for making continuous magnets. That will be enrolled on the vacuum chamber that we can see up there, and just by drawing with the laser and removing some material off the tape, we'll basically get the same result as what is in the top right corner, but in a much simpler way. This is for fusion, but this is not only for fusion. Why do I say that? Well, imagine that there's a lot of applications where we talk about magnets, and the flexibility of drawing patterns on those carpets allows us to potentially supply magnets for other applications. I have listed a few here. The main difference between what we call power grid application and pure magnet application is that in one case you need a low field, a no magnetic field, and then you can stay at relatively high temperature with respect to cryogenics. On the other side, magnets, you need high field, and then you have to go even at lower temperature to get the best performances of these materials. And so just to give a few examples, we have superconducting cables, we have current limiters for the power grid applications, and for the magnets, of course, we have the fusion magnets, but then we have energy storage, medical imaging for MRI, for example, wind generators. On top of the turbines, you have a stator and a rotor. Those are magnets, and so they can be simplified by using our HTS technology. Levitation trains, big science and accelerators, they all benefit from our technology. I was mentioning before, it's a bit simplistic, of course, these animations, but simply by drawing different patterns on these carpets, we can get to the requirements that each and every application needs. Of course, top left corner out of the 4 sketches, we can always go back to the current pattern. So we can take a big carpet and cut it down and have the 1 centimeter tapes which are used today. So we're not only covering what's done today, but we are expanding the spectrum of applications. And I think in this sense, this is the core of spill-out technologies, expanding the areas and the applications that we can look into. If we move on to liquid metal technologies, these are more niche, but they still are relevant for what we do at Renaissance Fusion. Again, this is an example of what we're building right now. It's the evolution of the first picture that I showed earlier, the first slide of the reactor. That one was using Gallinstan, which is an alloy which is very simple to use because it's liquid at room temperature. In this case, we're using tin, and so you see that the complexity of the machine, of course, is increasing because we need to heat up tin to make it liquid and then propel it through the machine. What does that mean? It means that we have to build our own liquid metal loops with pumps and diagnostic systems, and all of these can have application in, for example, liquid metal and molten salt cooling system. So the Gen 4 fission, for example, can benefit from these. And one thing that I didn't mention yet is that the final goal is to move from Gallinstan, that we used in the past, tin that we have to use right now, to lithium blankets. Why? Because they breathe, because they extract the heat, and because they protect the solid walls. And so, of course, we'll need to be able to ourselves to separate lithium, from to separate tritium, but at the same time we'll generate some enriched lithium. And so, again, that has application in neutron shielding, in tritium breathing, and in molten salt fission reactors. There's one last point that I want to mention, which is, well, actually, this is a list, just a list of to show that the interest in there, the traction is there, when presenting these solutions to industrial players, the interest in there, and on many different applications. I wanted to give an overview of what talks we are engaging right now with industrial players. One thing that I wanted to mention is that within the fusion industry, there might be spillouts, and it's something that sometimes it's a bit neglected. Why do I say so? Because I mentioned HTS magnets, I mentioned liquid metals. We're not the only startup that uses these technologies, quite the opposite. If you look at the startup space, and I have a few examples here, a lot of them are using coils, which are HTS-based. A lot of them are using liquid metals, different type of liquid metals, but the fundamental science is similar. And so there is, even within the fusion space, there is opportunities for synergies, for cooperations, and for spillouts, as we've been discussing. That was it. I thank you for your attention, and I leave the floor to Fred.